So we've seen that there's some issues with first normal form. We get these anomalies that we need to be able to deal with. And the way we're going to approach that is going to second normal form. So let's talk about that for a while. There's a little bit of backstory here before we can really talk about what second normal form is about, and it's also going to be applicable for third normal form. But I just want to give you some terms here that we're going to use throughout. The first of these is the idea of a super key. Now we're familiar with the notion of a primary key, and we'll see that primary key actually is going to show up here later on. But we want to give you some context to that notion of a primary key. So the first thing to think about here is a super key. And this is basically, so if you think about a particular table, and it's got a collection of attributes. This is kind of the relational algebra terminology, but you could think of it as the different columns in a table. So what we're looking for is a set of attributes, a set of columns, in which no two of the rows in that table have the same values. Or if we're thinking in relational algebra terms, no two tuples have the same values for all of those attributes that we've chosen. So the upshot of the fact that they're different in each of the tuples in the relation, or the rows in the table, means that those attributes, or those columns, can be used to uniquely identify a tuple. And that's really the principal purpose behind identifying a key in a database or in a relation, is being able to specify a specific tuple or a specific row in that database. Now, the important thing to keep in mind here, and the reason that you might not have thought about this idea of a superkey before, is that it's not necessarily minimal. In other words, we might choose 5 attributes out of a relation that just happen to uniquely identify all of the tuples in that relation. But if we throw one of those away and only consider the remaining 4, those 4 might also uniquely identify the tuples in the relation. So a superkey can be a way to uniquely identify a tuple, but it doesn't have to be the smallest list of attributes in order to be able to do that. You can actually see that the set of all attributes is a kind of a trivial superkey. Particularly if you keep the relational algebra in mind, remember that a relation is a set. So if we have duplicates, or we can't have duplicates because it's a set. If we happen to try to insert another tuple into that relation that had the exact same values in all of the attributes as an existing tuple, basically the result of adding that new one would be exactly the same set, right? Because the duplicate kind of gets tossed or gets thrown away when we try to add it. So trivially, we can use all of the attributes as a superkey. But that's not really very interesting, right? We're basically saying we can uniquely identify a tuple by giving the tuple. Well, okay, that's fine, but we're not really getting any bang for our buck there. So once we have thought about the superkey, the next idea is that of a candidate key. So by candidate, we're kind of indicating, hey, this is something we might actually want to use as a key. That's just not this kind of goofy super generic definition that a superkey gives us. So a candidate key is a superkey that has a minimal set of attributes. In other words, for a given candidate key, we can't throw away any of its attributes and have it still be a key. In other words, have it still be a set of attributes that will allow us to uniquely identify a particular tuple within the relation. So no proper subset, right? An improper subset is just the same thing. But proper subset means removing things from that set of attributes. So no proper subset is also a candidate key. So if we throw any of the attributes of a candidate key away, it's no longer a key of any kind. It doesn't uniquely identify rows. So the coming up with a list of all the candidate keys is actually kind of an important consideration when you're thinking about what do you actually want to use as the key to this particular relation. So a set of candidate keys of all of the keys captures all the different ways to uniquely identify a tuple. And again, that's just this same idea of a candidate, right? These are the possible keys that we might want to be able to use to identify unique values within this relation. Of those candidate keys, we can basically choose any one to use it as our primary key. So we've we come back to this more familiar term, the primary key. It's just some candidate key, right? Here's all the candidate keys. We could use any of them to uniquely identify a tuple, and we're just going to pick one. And oftentimes, the one that we're going to pick is pretty evident. You're going to choose like a numeric ID or a social security number or an international standard book number for a library database or something like that. It's not quite as abstract as what we're describing here, but we want to get some of these definitions in place so that we can talk more precisely about what second normal form and third normal form are. So that kind of completes the discussion of different keys. But we also want to think about individual attributes within the relations or individual column within the table. So there's two different types. The first is called a prime attribute, and this is an attribute that's in at least one candidate key. So you can have multiple candidate keys. They're all uniquely identifying a particular tuple in the database or in the relation. And they're minimal, right? There are no subsets of those keys that also exhibit that property. So we might have several candidate keys for a particular relation. And if we take all those candidate keys and we sort of take the attributes that are in all of those keys and group them together, or union them together, right? That set of attributes, or columns, right, if you're thinking in terms of tables, form what are called the prime attributes. So a prime attribute is just one of the attributes that's in that set of all of the attributes used in candidate keys. And then by negation, a non-prime attribute is an attribute that isn't in any candidate key, right? So prime attribute, an attribute that's in one candidate key at least. Non-prime attribute is an attribute that's not in any candidate key. Apologize for this flurry of definitions, but these are all kind of ideas that we're going to use as we talk about how second and third normal form work. All right, so given that terminology, let's turn our attention to perhaps the fundamental idea associated with second and third normal form, and that's the idea of a functional dependency. And this is a definition. It's quite generic, and we'll get more specific as we go here, but a functional dependency is a constraint that describes a relationship between attributes in a relation. And before we dive into the kind of the formal definition of this, let me just give you an example. A simple example would be that of a primary key. So if we go back to the first normal form version of our employee database, we had a employee ID that was used as a primary key to give us information about a particular employee, and that included the employee's first name and last name. So when we talk about a functional dependency, we're saying basically that the first name and the last name of that relationship, of that table in the example we were looking at, is dependent on the primary key. So that's how this idea of a constraint comes into play. If we know that the primary key is determinant of the values of all the other columns in that table, we can say that the value of the primary key kind of constrains the values of all of the other attributes that go into that relation. Okay, so that's one example, just to kind of give you a little bit of a mental coat rack to hang this on. So let's come up with a little bit more formal definition here that we can then use to look at some specifics. So we're going to just assume some relation R, right? So you could think about the employee database if you want, or the order database that we've been talking about. So R, that relation, has some attributes in it, right? The first name, last name, employee ID, hire date, whatever it happens to be. That has a collection of attributes, and we're going to use the variables X and Y, our identifiers X and Y, to represent subsets of those attributes. So that's just some group of attributes drawn from all of the attributes in relation R. And here's the kind of the definition of this idea of functional dependency. So we could say that the attributes in Y are functionally dependent on the attributes in X if, given the particular values for the attributes in X, we can determine the values for the attributes in Y by looking them up in any tuple of R that has those values for X. Now, to give that some specificity, let's go back and think again about that relation with the employee ID and the first and last name. We might, to flesh out this definition with some specifics, we would say, for example, that X could be the set of just one attribute, which would be the employee ID, and Y could be the set of two attributes, which would be the first name and the last name. If it's the case that Y is functionally dependent on X, then if we look through that relation and find a particular set of values for the X attributes, in this case just the employee ID, that uniquely will determine the value of all of the attributes in Y, in this case the first name and the last name. And we could look up that same dependency in any tuple of R that has the values that we've found for X. Now, in this case, the example is kind of trivial because X is just the primary key of that relation or that table. So it sort of naturally follows that anytime you see X, a specific value for X, for the employee ID in the table, it's going to uniquely determine the values for the first name and the last name. But this is more general than that idea. If it so happens that you have some set of attributes where any place you find those attributes in what we might call X, that if you look in another set of attributes that we could call Y, the values in Y would have the same values in those tuples that had the specific values for X. So it's more general than just this kind of primary key relationship, but I'm kind of trying to back us into the definition here by thinking about something that we're a little bit more familiar with. There's some other terminology here too. If we've been talking about Y being functionally dependent on X, if that's true, then we can also say that X functionally determines Y, and that's written in this area as X arrow Y. So we know something for X, and that implies something about the values that can be in the attributes that are part of Y. And again, keep in mind that X and Y are both sets of attributes. And because this is such an important relationship, we also have a special name for the thing on the left-hand side of the arrow. We call it a determinant, not related to the determinant in linear algebra. It's just because this determines something, it's called the determinant. Finally, then, we have enough information to be able to define second normal form. First of all, remember that the normal forms kind of build on top of each other. So if something is in second normal form, by definition, it's also in first normal form. And we'll see that if something's in third normal form, it's also in second normal form and first normal form. So that's the first element of the definition, is if we've got something that's not already in first normal form, the definition of second normal form doesn't really mean anything. So we kind of first have to be in first normal form. Then the specific definition of second normal form, given that we're in first normal form, is that every non-prime attribute is functionally dependent on the whole of every candidate key. So now all of those definitions kind of come back to haunt us here. Remember that the non-prime attributes are those attributes that aren't in any of the candidate keys, okay? And that the candidate keys are the ones that have kind of a minimal set of attributes that determine uniquely a specific tuple within the relation or a specific row within the table. And we want those non-prime attributes to be functionally dependent on the whole of every candidate key. In other words, when we're thinking about the definition of functional dependency here, if we say that X determines Y, X in this case is going to be the attributes that are in some candidate key, and Y is going to be each or all of the non-prime attributes. So we want that relation to hold between the non-prime attributes and the whole of every candidate key in order to determine that a particular relation is in second normal form. If that doesn't hold, that second constraint, then we don't have a second normal form relation. And this notion that the non-prime attributes need to be functionally dependent on the entirety, the whole of every candidate key, is where we get this other kind of silly saying that we use to distinguish these normal forms, that it's not just dependent on the key, which is first normal form, it's dependent on the whole key, which is second normal form. Not only does this definition of second normal form give us the details of how we can tell whether a relation is in second normal form or not, it also gives us, a little bit implicitly, but it gives us a procedure for taking something that is in first normal form but not in second normal form and creating a second normal form version of that. Essentially what's going to happen is if we have areas of the first normal form relation that violates that second constraint, in other words, we've got non-prime attributes that are not functionally dependent on the whole of every primary or every candidate key, that's a signal that we should separate the attributes of the original relation into multiple relations where that constraint holds, where every non-prime attribute is functionally dependent on the whole of every candidate key. So let's take a look at that in the order relation that we were looking at before. So again, I've duplicated the attributes that are in the order relation, and as I sort of alluded to before, I've kind of smuggled in our path forward by the way that I've listed these, and here I've just made it even more explicit with separate bullets. So we can see that there's really three kinds of underlying data in this order relation that are going to end up splitting into customer, order, and item. But if we think through kind of what are the functional dependencies that are going on here, I've listed the first three are kind of apparent here. So customer number functionally determines the customer's first name, last name, street address, city, state, zip, and phone number. Right? If any place I see in the order relation, I see a particular customer number, I will expect that the values for the first name, last name, and other customer-specific details are the same given that customer number. Right? I'm not saying anything necessarily about primary keys or whatever, but because I know that customer number is a candidate key, right? It was one of the ones that we identified before when we were talking about first normal form, and I can say that this functional dependency exists. Given the customer number, I would expect that any row of the order relation that we're starting out with, where I find that customer number, I would find all of the same values for these other attributes. The same thing is true for the item number. Any place I see the item number, I can say that functionally determines the description and the price, because those things should correlate with one another. It's kind of it's an obvious kind of way of defining these terms and these attributes of our data model to say that the item number, if I know what the item number is, well, I should be able to look up the description. I should be able to look up the price. So anywhere in that order relation where the item number appears, I should be able to see the same value for description and price. And then finally, the same thing for the order number. Order number, if I see that any place, that's going to determine the order date. So we can see if we go back to the definition of functional dependency that we are following this definition. The thing on the left-hand side of the arrow is some set of attributes, and in this case, the examples we've considered so far, it's just one of the attributes. If we know the value for that attribute, given the value x of the x attribute, we can determine the values for all the attributes that are in y by looking them up in any tuple of R that has those particular values for the x attributes. So if we go back to here, any place that I look in this order relation, and remember that order relation at this point has all of these attributes in it. So any place where I look in the order relation and I find a particular customer number, I would expect that the values for these other attributes would be the same for the same customer number. And similarly for the order number and the item number. So those definitely follow the definition of a functional dependency. At issue here, though, is that we've been able to identify those functional dependencies, but we are not satisfying the definition for second normal form. This says that every non-prime attribute has to be functionally dependent on the whole of every candidate key. Well, the non-prime attributes here are the ones that basically these ones, right? The ones that aren't one of those customer, order, or item numbers. So by the definition, every one of those non-prime attributes has to be functionally dependent on the whole of every candidate key. Well, these ones, first, last, street, city, state, zip, phone, are certainly dependent on customer number, the candidate key, right? That's what's expressed by this functional dependency. But we have other candidate keys present in the order relation. We have a candidate key that's called item number, one called order number, and one that combines the item number and the order number. However, these attributes, these non-prime attributes, are clearly not dependent on the item number or the order number, right? So because we have non-prime attributes that are not functionally dependent on the whole of every candidate key, this relation is not in second normal form. However, this notion of functional dependency also gives us some idea about how do we convert it into multiple relations that are themselves in second normal form. We basically can use this information of the functional dependencies to partition the order relation into smaller relations that do respect this functional dependency. So, and this may have been obvious to you from the beginning if you've done any kind of database development, we're going to split this apart into a customer relation, an item relation, and an order relation. And because we're going to basically move the other attributes, both the candidate keys and the non-prime attributes that aren't dependent on the candidate key in the particular relation we're creating, that's going to make the resulting relations be in second normal form. Let me take a quick look at this fourth functional dependency. What we're asking here is what determines whether something has shipped. And it's evident if you think about it for a little while that just knowing the item number doesn't tell us whether or not that particular item has actually shipped with a particular order, nor does just knowing the order number let us know whether that particular item has shipped, because there might be some items on the order that have shipped and some that haven't. So it would not be sufficient for us to include has shipped as a non-prime attribute in either the item number functional dependency or the order number functional dependency. In fact, we need to have both of those attributes as the determinant for this particular functional dependency, because if we have either of them missing, we don't know the value of has shipped. So let's now take a look at a refactoring of this order relation into multiple other relations that are now going to be in second normal form. And as I suggested before, these four functional dependencies are what are going to guide our choice of relations that are going to be in second normal form. And here's that list of relations. We've got a customer relation, and as you can see here, the highlighted customer is, or the highlighted attribute is the primary key, and we've got the attributes that we saw from the right-hand side of that functional dependency, and the same thing here for the item relation and the order relation. These are exactly the same fields that we just saw back here in these first three functional dependencies. And then for the order item, we've got a composite primary key that's composed of the two determinant attributes in that functional dependency, and then the has shipped. Now, if we go back and kind of reflect on whether or not we've advanced our case here by going to this second normal form, we can go back and kind of think about the anomalies that we identified before. So from the perspective of an insert anomaly, we can now insert any of these things, customer, item, or order, completely independently of one another. There's no restriction any longer that says, for example, I can't add a customer unless they've already placed an order, because these are now independent relations. So my sales staff can go out and sign up customers all day long, whether or not they've ordered anything yet, and then I can go back and associate orders with them as necessary. So I've dealt with some of the key insert anomalies. I also now can delete things without adversely affecting other parts of my data. So I can, for example, delete an item. Maybe I have an item that I've had in my catalog for a year and nobody's ever bought it, and there's no point in carrying it in my warehouse any longer. Well, I can just get rid of it here, and that's not going to eliminate any other data that might have included that item. And then finally, I've eliminated update anomalies, so I can update any of the values of particularly the non-prime attributes here, right? If somebody changes their phone number, I don't have to go find every instance of that customer in all of the rows of my original order table. I just have to go find the one place where that customer's details are stored in the customer relation and change their phone number. It only exists in one spot. Now this example has kind of grown here, so rather than looking at this in more detail as we head toward third normal form, I want to suggest a different example. So here's a new relation. It's called item. It has an item number and then a description of that item, a distributor number. So this is like an identifier for the distributor that ships this item, and if we're like a retailer, we might be using these distributors and we want to know where to order them from. And then because we want to be able to contact the distributor to ask them to order or to send one of the items that they've got in stock, we need their phone number. So we've got an item comes from one distributor. These are just kind of a business rule associated with this little application. A distributor just has one warehouse, and that warehouse has one phone number. So the question to start out with here is this relation in second normal form? So maybe pause the video, take a second, and ask yourself if it satisfies the constraints associated with second normal form. So yes, in fact, it is in second normal form. In particular, we can say that we have a functional dependency of all of these attributes here on that item number. So and I've already kind of flagged this as the primary key for this relation, but we're basically saying that the value of item number functionally determines the description, the distributor number, and the warehouse phone. Because if I know the value of that item number in any place it might appear in a relation, I'm going to also have the same value for the description, distributor number, and warehouse phone. Okay, so it is in second normal form. It's also in first normal form, right? Because we know that anything that's in second normal form has to be in first normal form. However, it's still subject to different kinds of anomalies. So here's I've reproduced the relation here. We have insertion anomalies. So I can't add a distributor, right? If I get a new distributor that I want to distribute products from, I can't add a new distributor until I have information about an item that distributor distributes, which is kind of not ideal. I also have a deletion anomaly. If I delete the only item from a distributor, in other words, if a distributor just has one item that I distribute, and I delete that item, then I've lost information about the distributor. I no longer know what their number is or what their phone number is, because those two things are conflated in this relation. And finally, I have a modification anomaly. If I want to go in and change the phone number for this distributor because they've gotten a new phone system, or maybe they've moved and now they have a new phone, whatever, that phone number is duplicated in every record, every item tuple. It's duplicated every place I see this item that's distributed by that distributor. So in order to change the phone number, I've got to go find all of the instances of this item number, or any item number really, from that distributor, and I've got to modify the phone number at the warehouse.